are built on the of the Huchian within the homeland of Chochenyo-speaking Ohlone people. We acknowledge and honor the Ohlone people who have lived in Berkeley throughout the East Bay and since time immemorial. The library recognizes that Berkeley residents have and continue to benefit from use and occupation of unceded stolen land, and we pledge to recognize permanence and the rich contributions that the Ohlone people continue to bring to the city of Berkeley and throughout the East Bay. We celebrate the strength of the Ohlone people and their culture. The Berkeley Public Library is committed to helping create a more just and anti-racist society and to furthering the visibility and celebration of Ohlone authors who are specific to the East Bay and Ohlone culture in our collections and programming. This is a living document that was co-written by Ohlone cultural leaders Vincent Medina and Louis Cravino and the Berkeley Public Library. So welcome to Popping the Science Bubble. This is a monthly seminar series that aims to share new research findings from grad students and postdocs at UC Berkeley with the general public and create constructive discussion about a variety of science topics. We have 2 speakers at each seminar who will talk about their current research or a topic that they find really interesting. The organizers are 2 graduate students at UC Berkeley, Kaylin Schwang and Daniel Brethauer. And this program happens every 3rd Tuesday of the month at 5:30 p.m. at the library and on Zoom. If you're interested in checking out their past seminars, you can visit their website and sign up for the listserv to keep in the loop for upcoming seminars. Also, check out their YouTube page to view an archive of past lectures. So thank you so much. Let our organizers introduce your speaker.
So thank you so much for being here, and thank you for the people who are currently on Zoom. We are very excited for today's speakers. So as Kelsey said, we host this talk every 3rd Tuesday of the month to try to get a wide variety of departments to share their interesting research with all of you. And so if you're interested in learning more about our future seminars, please join our listserv using the QR code that we will be posting at the very end of this, or you can go to our website, poppingthesciencebubble.com, or bit.ly/ptsb emails. And so for tonight, we're very excited to have Dhruva Ganapathy and Sam Oakes-Leaf with us to present. And so this is the open format. So please, if you have any questions, feel free, raise your hand during the presentation and go ahead and ask them when the presenter calls on. For those of you who are on Zoom, if you would like to, please submit your questions through the Q&A section, and we'll ask it either in real time or at the end. And so to start us off, our first speaker is Dhruva, who is a postdoc in the physics department at UC Berkeley, working on optical atomic clocks. He got his PhD from MIT last year, where he worked on gravitational wave detection. And outside of research, he likes to make music and go to concerts. So without further ado, please take it away.
Okay. Hi everyone. Is it okay if I just sit?
Yeah, absolutely.
That's right. Yeah.
Okay. So yeah, I guess you can keep it pretty informal. Feel free to ask questions in between. If you want me to go back or forward a few slides, that's also fine, because I don't think this presentation is as structured as I would like it to be. Okay. Yes, I have already been introduced, but here's a shot of me in full clean room gone in front of a lot of expensive optics. Yeah, so I'm in the physics department. I work on atomic clocks. I got my PhD last year from MIT, and where I work in gravitational wave detection. And I'm going to be talking about why physicists are very interested in measuring small things. It's a field called precision metrology, where we try to make more and more precise measurements. And I thought I'd give some historical context for this. Now, the field of precision metrology itself is really old. I mean, it's as old as when people looked to the stars and tried to figure out how far we were from other planets, how far we were from the sun. But that would make the talk like infinitely long. So I'm going to start in the late 19th century. And I thought that this quote was probably a good quote to start with. It's been attributed to Lord Kelvin, saying there is nothing to be discovered in physics now. All that remains is more and more precise measurements. I thought that, wow, this is a great quote to start the talk with, because, he's been proven wrong. Turns out he didn't actually say this. Just like many other quotes in science, this is apocryphal. I'm like, okay, this kind of ruins the whole premise of my talk now. But I'm still going to focus on this one last line. All that remains is more and more precise measurement. And this is actually very similar to an actual quote that was made by another physicist called Albert Michelson. He said an eminent physicist, maybe he's talking about Kelvin, maybe he's talking about someone else. Remarked that the future truths of physical science are to be looked for in the sixth place of decimals. Now, this is actually, I think it has a bunch of truth to it because, and as I will show, during the turn of the century, people got very interested in the spectrum of hydrogen. Now, what hydrogen is one of the simplest things you can think of in physics. You know, if you wanted to make precise physical measurements of something, hydrogen is the simplest system you can get. We can ignore the other two isotopes, but the normal hydrogen that we're familiar with has one proton and one electron. And any two atoms of hydrogen will be exactly the same. So hydrogen has something called a spectrum. Basically, you shine light at hydrogen and it emits light of its own, which can be separated out into these very specific wavelengths. This was found in the late 1800s. People had seen the spectrum of hydrogen. People didn't know where it came from. This guy, Johannes Rydberg, came up with some empirical formula. But it was only theoretically explained by Niels Bohr later, and this marked the birth of quantum mechanics. Bohr basically said that these different energies come from the fact that hydrogen has like discrete energy levels, and whenever an atom jumps from a higher energy level to a lower energy level, it'll emit a photon that corresponds to the energy difference between them. Okay, that in and of itself is kind of boring. But the interesting thing here is if you look at this line over here, the 656 nanometer line, if you zoom in a lot, you actually see that it's split in two. This measurement was actually made much before people actually understood where these came from. It was made by the same Michelson guy and someone else, probably. I won't go into how the measurement was actually made, but you can kind of see it here in these rings. You see like two separate rings at every order over here. And this kind of corresponds to the fact that there are actually two different wavelengths over here. And this was a pretty big mystery when, people, especially once people started getting around to figuring out how hydrogen works. This guy, Sommerfeld, he called this the fine structure splitting, sort of mix some constants of nature together to get this fine structure constant, which kind of defined how much these lines are split apart by. But it was only when this guy Dirac came up with a relativistic treatment of quantum mechanics, where he combined relativity, Einstein's special relativity, and quantum mechanics, that this term, the fine structure constant, popped out naturally. I will say that where this actually comes from in nature is far more complicated than just what Dirac's treatment of it. It's still an open question. If you go to Wikipedia, you'll see a whole page about what the possible interpretation of the fine structure constant are. Not good enough. Okay, but an interesting thing here is now you can actually look at the hydrogen spectrum with this fine structure splitting, and you can zoom in even more. So you see a factor of 10 below the fine structure splitting, there is yet another splitting, and this is known as the Lamb shift. It was first measured in 1947 by this guy called Lamb, and everyone else is that student. Now, clearly people hadn't seen this before because the experiments weren't good enough. But once the experiments got more precise, they found this little shift. And it took a while for people to figure out where it actually came from, but then a bunch of people worked on this and saw that this is actually due to quantum electrodynamics, and which is sort of the modern form of quantum mechanics that says that, well, everything like, particles, forces, everything can just be thought of as a field. And that when you start putting in the math and cranking the engine, you'll see that there is this small fine structure splitting. Similarly, there's another split that's a factor of 10 below the fine structure, and that's called the hyperfine structure. This because of how the spins of the electron and the nucleus interact with each other. If they're in the same direction, the atom has some kind of energy. If they're in the opposite direction, it has different energy. and that creates the splitting. It was measured first in molecules by I.I. Rabi, but that's a more complicated measurement. No one really knew what they were seeing then. In hydrogen, it was actually first measured through astronomical measurements. This is a very famous, the light that's emitted when an atom falls from one hyperfine level to another is a very famous line. It's called the 21 centimeter line. And because there's hydrogen everywhere in our galaxy, people have used the 21 centimeter line to make maps of our galaxy. Okay, so I guess enough about hydrogen. But what I'm trying to underscore here is that precision measurements are important. New and precise measurements which deviate from current predictions can stimulate the development of new theories in physics. Conversely, if we do have a new theory in physics which hasn't been confirmed, it's quite often that we need to just make more and more precise measurements to confirm or disprove these theories. It's been pretty important in the last century. Here are a few examples of where precision measurements have led to sort of significant advancements in physics. I'm not going to go into a lot of detail about this, but I'm sure a bunch of you remember the discovery of the Higgs boson a decade ago. It made big news, even though theory itself was something that Higgs came up with, I guess, in the 60s, 50s or 60s, something like that. It's just we needed to work on technology and get our experiments to be precise enough to measure this. Okay, now I'm going to talk about my own experience with precision measurements. So for my graduate research, I work in gravitational wave detection. I'm going to show a few quick videos to show what gravitational waves are. Now, Einstein's theory predicts that whenever there's a system with some sort of asymmetry in its geometry, it'll produce gravitational waves. A very classic example of this is when two black holes are colliding with each other. So you can see these two black holes are spiraling into each other. And as they do so, they're sending ripples out into space, which stretch and squeeze space. So as they come closer together, the frequency of this gravitational wave goes up, and that's known as a gravitational wave chirp. Eventually, these will merge, and the system will settle down. Once this gravitational wave reaches Earth, it's going to basically stretch and squeeze space just a little bit. Obviously, things is vastly exaggerated. This is not actually happening right now. But just in order to represent what kind of effect we're looking for space stretching and squeezing. Yeah, so how do we make measurements? Okay, sorry. Just for context, how much space is actually moving? It's moving by like a billionth of an atom. Yeah, it is a billionth of an atom. So give some context. If we keep zooming into an atom, a typical gravitational wave will produce a length signal, which is only about this much, which is ridiculously tiny. So how can we hope to measure something like this? We use this principle called interferometry, which is basically you take a laser, you split it in two, you reflect it back from two mirrors, and based on the difference between these two parts, it will either add up or subtract on this output port. This is known as constructive or destructive interference. So by measuring how much power is coming out of the output port, you can sort of measure how much the path difference between these two parts is. And if we have a gravitational wave that comes in and distorts these parts, we can see that as a power signal. In reality, this is a very difficult experiment to do. The two gravitational wave detectors in the US are the two LIGO sites, the Laser Interferometer Gravitational Wave Observatory. There's one in Livingston in Louisiana. There's one in Hanford in Eastern Washington in the desert. I spent 1 year of grad school over here. It's an awful place. Not the people are great. It's just Eastern Washington's pretty awful. But yeah, after decades and decades of work, we finally measured gravitational waves in 2015. I say we, I was still an undergraduate, but yeah, so that just shows that, Einstein predicted this in the 30s that there'll be gravitational waves, and it took 7 decades for us to actually eight decades for us to actually measure them. Now I'm not gonna go into the details of what I did when I was on site. I can say that I worked in a very specific subsystem that was that had to do with reducing quantum noise. What I can do in limited time is show you some pretty cool pictures from site, just to show that to make such a, even in one subsystem of this really complex instrument, there's so much to do. And this just shows us how much work we need to do to actually make these super precise measurements. Also, I would like to point out that it's not unlike those like early 20th century examples where, you know, it's one guy who comes up with something and the other was like, oh yeah, I found this in my basement. It's actually like there's thousands of people working on this because these experiments are hard. And apart from confirming the gravitational waves exist, LIGO's measurements have been very useful for astrophysics. This is an interesting plot. I just focused on the fact that the black holes we knew of using methods other than gravitational waves, which I guess usually X-rays, X-ray binaries, are much smaller than the ones that we measured with gravitational waves, which just tells us that before we had gravitational wave measurements, we didn't know black holes could get so big. So that's led us to have more open questions in physics. How is it that black holes get this big? Because astrophysics says they actually shouldn't, at least when they're produced. So it's quite interesting. So that's just saying that, you know, making precise measurements has opened a completely new window into the universe. Yeah. Another pretty interesting example is before gravitational waves, we thought that most heavy elements came from exploding stars. Now we know that most of them actually, like most of these elements, these purple ones, come from emerging neutron stars. So in that way, you know, making precise measurements has enabled us to find new physics. Am I doing on time? So now I'm going to really quickly talk about atomic clocks because that's what I'm working on now. So remember that hydrogen spectrum I was talking about. Well, turns out when an atom emits a photon, if the frequency is precise enough, you can use that as a reference. Like basically an electromagnetic wave is something you can just like, if you reference it to an oscillator, if you like measure the time between two crests or two troughs, you have a frequency reference. And that basically means you can use it as a clock. The first useful atomic clock was a cesium clock built in 1955. That's the current timekeeping standard. Yep.
So since you had mentioned before that hydrogen has that fine splitting and hyperfine splitting that kind of shifts where precisely this wavelength is, does that have an impact on our ability to measure the clocks?
So yeah, there's two things about a clock that are important. One is what the frequency of the clock is. And the frequency is just defined by what the transition is. So if I was hypothetically saying using hydrogen as a clock, I would see, if I had a precise enough measurement, I would see two separate frequencies. So that would tell me that, okay, I'm going to use only one of, like, you know, I'm going to use only one transition as my frequency reference. But there's another thing which is quite important to clocks, is the inherent stability of the frequency itself. And that's something that is sort of decided by nature. It's decided by quantum mechanics, is that if the transition is not very long-lived, it's going to have a pretty significant line width. So the frequency will keep changing with time. And that's the reason we can't use hydrogen as a clock, because its hydrogen line widths are really large compared to any useful clock. Cesium, on the other hand, was a good starting point for us. And it's the standard now. Our definition of what 1 second is based on the number of times we can measure oscillations in this hyperfine transition in cesium. That's where we're actually using the hyperfine splitting in cesium, because that's something which is at microwave frequencies and we can directly reference it to electronics. And yeah, there's this unholy number over here, which just corresponds to the frequency. And it's like, okay, that's the frequency. Let's just say that this many cycles of the cesium transition is 1 second. And that's how we define the second now. The current state of the art clock is strontium. Now, unlike cesium, which is at microwave frequency, strontium is at optical frequencies. It's actually much harder to make an optical clock. That's why it's not the standard. You can't like have everyone have one strontium clock, which is reference, because you need a whole lab to do it. Now, a strontium clock, the stabilities that have been reported are pretty ridiculous. So, as I've written here, if you had two state-of-the-art strontium clocks that started when the universe was born, by now they wouldn't be off by a second. So that's how stable they are. And because they're that stable, we can use, it's an extremely good platform to do precision physics. For example, it's been used to measure the time dilation due to gravity at the scale of a centimeter. I'm guessing people see in Interstellar, where you see 1 hour here is 7 years on Earth or whatever. That's highly exaggerated. You need very unphysical black holes to actually do that. But this is a real thing, like time dilation due to gravity, and we have measured this at the level of a centimeter, not because there's a lot of time dilation. That's because our timekeeping references have become so precise that we can actually measure, like, you know, 1 part in 10 to the minus 19. So yeah, we plan to use this platform now to conduct further tests of gravity, look for dark matter, and potentially detect low frequency gravitational waves by putting them in space. Here are some pictures from an atomic clock experiment. Unlike gravitational wave detectors, which mostly work in infrared frequencies, we're kind of lucky in atomic physics. We have all these visible wavelengths. There's a whole lot of blue here, there's some amount of red, there's some green, which is not in these pictures. We've recently got a laser, which is a nice teal color. So it's quite fun to be in the lab with all these lasers. Going ahead, there are a bunch of open questions in physics, like, you know, where is dark matter? Why is there more matter than antimatter in the universe? This is known as the strong CP problem. Why isn't gravity compatible with the standard model of particle physics? And in order to answer these questions, we at some point have to make incredibly precise measurements. And that's why precision measurements are important to physics as a whole. So yeah, precision metrology is the key to understanding how our universe works. They're generally at the cutting edge of technology, and there's so much about physics that we don't know, which is good, because if we did, I'd be out of a job. And I also would like to mention that I've been incredibly privileged that I've gotten to work with a lot of people, and I think this is how science is done. It's done as a community. So yeah, I know that I might have spent like the first few slides, you know, singling out individuals, but that was like an early 20th century thing. We don't live there anymore. We live in the modern day, and it takes a lot of people to do good science. And it's the people that make it worth it. So, questions?
Let's do a round. I would also love to know a little bit more about like what exactly you're working on now. Is it trying to make your measurements of the frequency from strontium more precise? Is it trying to beat down noise? Is it, you know, what's
so yeah, let's see. One thing is, I mean, there's two parts of it. There is trying to make our clock better, which is make it more stable, make it stable over longer periods of time, so that we can average down better, we can make more precise measurements. But also there's a bit about trying to make more creative measurements. Like, you know, like at the end of the day, it's a clock, even no matter how precise you make it, it's a timekeeping reference. It's up to you to figure out what to do with it. So that's something which what we're looking into right now. What all can we do? What tests of fundamental physics can we do? You know, if we do say want to look for things like ultralight dark matter or something, how would we design an experiment that incorporates these clocks to to make the most useful possible measurement. Then there's this whole thing where, like, you can use this as an alternative to other future space-based gravitational wave detectors, where if you put a bunch of clocks into space, you can basically create a network. I guess I can use astro terms with you. You can use it to better localize your signals, because if you have a network compared to like LISA, which is just one detector, so you can use the localization. Its clocks make it pretty easy for you to tune the bandwidth of your detector. You can it's just by changing the measurement protocols, you can actually change where your sensitivity is, so you can actually have it follow gravitation. So that's something I've been looking into. And then other things like gravity for sure. So the idea of strontium clocks are now being used in something called atom interferometry, where, like I showed laser interferometry before, you can do the same thing but with atoms. Just split an atom into a superposition of two wave packets and then recombine them. And both of them, if they're sensitive to different gravity, they can measure signals from gravity. And that's essentially trying to measure gravity at like the smallest quantum scales possible. So that's something that's a pretty hot topic in at least precision atomic physics. But yeah, a lot of the day-to-day work is just trying to hunt down random sources of noise, trying to like remove this one electrical buzz somewhere. Yeah, so essentially what I'm doing right now is, one, I'm trying to figure out how clocks work, because I'm still pretty new to this. It's been about half a year since I started my postdoc. I had no atomic physics experience before this, so that's kind of what I'm focusing on, is getting familiar with the system and really try to make it better and come up with more interesting measurements.
This is very cool. And like you mentioned, with achieving this like time precision is very significant, crucial. And I'm assuming, to perform the like most ideal experiment, there's other things that you also want to measure with great precision, right?
Yes.
And so can you talk about what are the current challenges or bottleneck to, with like kind of precision, like is it, the ideal to match up with the precision that you're able to achieve with time, or is time precision kind of catching up with other, precision, or what's the kind of state of precision?
Yeah, I can. So in any experiment, we're just trying to look for any sort of physics. There's essentially two parts. There's a signal and there's noise. And there's two things we want to do. We want to make the signal as big as possible, and we want to make noise as small as possible. Within the noise, there are things that are statistical, which we just need to average more of. So if we say, there's something called quantum projection noise. If we use 100 atoms, then we're just limited by the fact that if we want to measure them in the superposition, it's limited by the fact that we just have 100 atoms to measure on. So more atoms makes that measurement better. We can make that even better by doing something called entanglement, which just create correlations between all of these atoms. So that's how we get around statistical noise. Systematic noise, like systematic shifts, on the other hand, are more complicated. But one example is this frequency that I was talking about, this absolute frequency difference. It depends on so many different things. It depends on what your magnetic field at your location is, what your electric field at your location, depends on what the ambient temperature is. And so one project I'm looking into right now is about in situ thermometry, which is basically trying to use other atomic states to measure what the ambient temperature at the atomic locations exactly are. And that will allow us to completely dial in what we call the black body radiation induced shift. So that's like, an important thing we can do, because we're only as good as the temperature we can characterize. Same with the electric and magnetic fields. Like, you need to be very good at characterizing these things. People have come up with very clever ways to get around this. There's one thing is that atoms themselves, the reason that strontium clocks are only coming up now and cesium clocks have existed for decades is because in order to do anything useful with strontium, you need to trap them. You need to trap strontium atoms for a significant amount of time. And trapping them requires really strong lasers. which these lasers are part of something we call an optical lattice. And this lattice itself, because it has so much power in it, it has its own electric and magnetic fields that are going to cause a shift in the frequency. So a decade ago or something, I think 2 decades ago, there was this concept of a magic wavelength that was introduced, which was for strontium's clock transition, just happens to be such that the shifts for both the states we care about are the same, so they get cancelled out. So it's just like, sometimes the problems are hard, you have to do better characters, and sometimes there are like these creative solutions you have to come up with. Now almost everyone using strontium uses the magic wavelength to trap. And our new teal laser that I was talking about is a new magic wavelength, which we've been meaning to try out. So,
you started to actually answer this question that our Zoom audience had. So they were wondering, do the lab lasers require a lot of electrical power, and how do you ensure that the power is not disrupted?
That's a great question. When I was in Lego, we had the institutional power of like $1 billion NSF grant behind us, so all of this was very easy to do. We just had a whole team managing our electronics. If we lose power, we lose power. I mean, we've had worse situations where people have just accidentally pressed the interlock button, like the emergency stop button on the laser, and it's like, oh no, takes 30 minutes to switch them on again, but that's fine. It's not a life or death situation. It's not like, oh no, the IC was running out of power. Similarly over here, I mean, there are some things which we keep connected to a battery or UPS, especially like our vacuum pumps, because we don't want them to stop working. On the other hand, yeah, we do need a lot of power, especially when we're trapping our atoms, not for the lasers actually, but that we have to create very strong magnetic fields to trap our atoms, and they need a lot. So yeah, but if we lose power, we kind of lose power. I mean, at the end of the day, like the experiment here is a small tabletop setup. It's not like, we'd start again once the power comes back. It's that simple. When we if we plan to put these things in space, then that's a different challenge altogether. I'm sure that'll be a good project for like starting grad student or an undergrad. How do you keep a constant power supply which is not going to be disrupted by any fluctuations or anything like that. So yeah.
Other question? Then let's thank our speaker again, and we'll begin the transition.
Thank you so much for the very interesting talk. And now it is my pleasure to introduce our second speaker, Sam Oaksley. Sam is a fourth-year PhD student in the chemistry department at UC Berkeley, working in the group of David Limmer. Sam grew up in New York and went to Brown University for undergraduate studies before heading out to the West Coast for grad school. In his no-research time, Sam likes to play basketball and the guitar, and is always on the hunt for a good movie. And so please take it away, Sam.
It says to choose to mirror or extend now. Says shared. No, not yet. I'll provide a minimum. And then can you also share?
Probably a theory. Let's study that. Am I gonna be able to get rid of it? Yeah.
Remember to share your screen too. There should be the option on the top.
Is this just shared?
Yes,
Right.
there we go.
Okay. Hi everyone, I'm Sam, as was mentioned. I'm a grad student, a fourth year grad student at UC Berkeley in the chemistry department. I also do some work at Lawrence Berkeley National Lab, or I have an appointment there. I'm a theoretical chemist. I do most of my work on a computer. So I've never actually been to the lab, and I don't spend much time in any labs, but I do think about trying to make materials or how you could make materials that'll be useful in technological applications. And specifically, I'm going to talk today about making materials on the smallest scales that we know how to make materials on. And on those scales, there's going to be really interesting phenomena that crop up due to quantum mechanics and things like that. And that's what I'm kind of showing in this picture off to the side here. So hopefully by the end of the talk, you'll understand a little bit about what this picture is trying to represent. And you'll understand a little bit about the field of nanoscience, which is my field, and that's what I'm going to talk about. So let's start by looking at something called the Lycurgus cup. I think I'm pronouncing that right. I've only actually heard it or seen it in writing. But it's a historical artifact that was, I think, somewhat puzzling to historians or to the people at the time, certainly, because it has a really interesting property that if you light it from the outside, it looks green, but if you put a light in the inside, it looks red or purplish. And it's confusing where that difference is coming from because it's all the same material. So you might think that different materials can have different colors, right? So gold is a different color than silver, is a different color than certain types of glass or whatever. It's a different type of color than wood. And so you might think of color as sort of a material property. It's something that's determined maybe on a small scale by the molecules in that material or the atoms. But it's not dependent on things like the size or the shape of the material, right? If I cut a piece of wood, it's still the same color as it was before. But it turns out that when you make things really, really small, their color can change with their size. And so years later, 1500 years after this cup was made, people analyzed it. And what they found was that there were actually really tiny particles of metal, mostly gold in this cup, on the outside and on the inside. And on the outside, the particles were on average a lot smaller than on the inside. And the difference in size between these two particles is actually what leads to the difference in color. And so that's a phenomena that's special when you go down to these really small scales. These particles are called nanoparticles because they're 1 billion times smaller than the macroscopic world. Okay, so my goals for this talk is to understand why that happens.
How were they able to get those tiny particles 1500 years ago?
I'm actually not sure. It's a good historical question. Sometimes I think, during certain, so when you make glass in certain types of ways, and this is actually one of the first ways that people synthesize nanoparticles on purpose, as sort of particles within glass. And I think during the making of glass, you can make nanoparticles by accident. I'm actually not totally sure exactly when that happens, to be honest. That's a good question.
Able to see.
But it wasn't intentional, right? So they weren't trying to make the nanoparticles back then. But nowadays people are, because we found out that there's these cool properties.
I'm just thinking maybe I should move so that I don't.
So my goals for the talk are to understand where this comes from. So why can you change the size of a particle and you change its color? And then to also understand a few reasons why that might be really useful for certain applications in technology and in material science. So nanoparticles, as I mentioned, are crystals, right? They're metals like gold or silver or cadmium or selenium, or cesium even, probably not cesium. I was just trying to relate it to the previous talk that we saw. But they're often metals. And so they're organized into crystal lattices, but they're built just one atom at a time. So the atomic scale is often 10 to the minus 10 meters. The name that we have for that is an angstrom. It's really small. So it's 10 times smaller than a billion. It's 10 billion times smaller than a meter. And the picture that we often have in an atom is like a nucleus surrounded by some electrons, as in there. And then you can put a bunch of atoms together in a molecule. So this is how you might draw a molecule in like an organic chemistry class. And so maybe you're putting tens of atoms together, maybe hundreds. And so you're going up a few or one or a few orders of magnitude in size. And then all the way on the other side of the spectrum, we have materials. We have here bulk gold, right? So we have macroscopic dimensions of materials. And for a long time, those were sort of the only two domains. So you could do chemistry on the scale on the left, right? Or you could even do physics on the scale all the way to the left on the atomic scale. And you could do material science on the right, on the bulk scale. But nanoparticles sort of lie in the middle. So there are many, many atoms, often thousands, tens of thousands, even hundreds of thousands of atoms. But in here, there's like 10 to the 23 atoms, right? So it's way, way, way fewer atoms than a material, than bulk, but way more atoms than a molecule. And so it's sort of lying in this middle region, and that's what gives it its special. And just to give you a sense of what the scale is, this is a good graphic that I stole from the Nobel Prize announcement about this field. And so on the left is a nanoparticle. That has the same relation in size to a soccer ball as a soccer ball has in relation to the Earth. So it's very, very, very small. It's still much bigger than. And so what we need to understand about when things get small is that the intuition that we have classically doesn't really work out anymore. So the picture I showed of an atom was a nucleus with electrons floating around it. But that's actually not the case. So if you saw the previous talk, you actually got a really great introduction to this already. Actually, in much more detail than I'm going to talk about it, but you don't have electrons that are orbiting the nucleus in a sense. You have orbitals. You have a set of discrete wave functions, is what we call them in physics, but a set of discrete sort of maps you can think of the electron, where the electron spreads out. And it spreads out in these very specific patterns, which is really cool. So the patterns all have a certain symmetry, right? The symmetry actually changes as you go down this list. And we give those names like S, P, D orbitals, which you might have heard in a chemistry class before. But what's really important is that the electrons aren't particles really. They're really waves. And they're really spread out across the entire atom. And that's what quantum mechanics tells us is true. And because they're waves, confining them can do an interesting thing. So when you put many atoms together to make a particle, so like the nanoparticles I was showing, each electron is still a wave. So you still have the electrons in this nanoparticle, this is the figure I showed on the very first slide, are still described by some function that's similar to the functions I was showing before. So some sort of wave-like pattern is one electron. But the wave can only spread out as far as the nanoparticle extends. And so that means if you make your nanoparticle smaller, you're confining the wave. You're confining the electron. And there's a really neat analogy here, and it's actually a pretty accurate analogy as far as things go, is that when you confine waves, you increase their frequency. So if you think about playing the guitar, oh, wow, I reversed my pictures there. That's unfortunate. If you have a shorter string length, right? So you bring your finger down the guitar, it's going to play a higher frequency note, a higher pitch note. So that should actually be the top picture, higher frequency. So the wave is closer together. And if you bring your finger up and give more space to the string, you're going to play a lower frequency note. So when you confine a wave, you change its frequency. That's an important principle that applies to the electrons because the electrons are waves. But just like the electrons have a frequency, different colors of light have frequencies too. So white light, the light that comes out of the light bulb, is actually made up of a bunch of different frequencies, all that are associated with a different color. And it turns out, or really it's a principle of physics, that you need to conserve energy. So if you're going to absorb light, the frequency has to match between the light that you absorb and the frequency of your electron, in some sense. But I haven't gotten into the details there, but that's pretty much true. And so that means that size will change the frequency of the electron, which will then change the color of light that the particle, right, or the material can emit or absorb. And the color that you see if you had a material with a bunch of particles in it, like I showed before, the Lycurgus cup, is just the color that isn't absorbed, right? So it's all the color that's reflected instead. And so the color that you see is directly related, in this case, to the size of the particle. That's how we can understand. And so that's a really cool property of physics, the really cool manifestation of sort of physics that you can see in the real world and that we can make in the lab. And it turns out it's pretty important. So it got the Nobel Prize in 2023 to these three people here. And the prize was for the discovery and synthesis of quantum dots. So I've been saying nanoparticle the whole time because I think quantum dots is a less accessible word, but it's also called quantum dots sometimes to emphasize that these are particles that are small enough that these quantum effects become important. And the reason it got the Nobel Prize is that those people that I showed in the last slide started making these particles and they figured out how to make them really well. And it sort of launched this whole field of nanoscience. So of making these types of materials, not just the particles that they made back in the 80s and 90s, but new types of particles that are also on this similar length scale. And those have been super useful in a bunch of different fields. One field being biomedical imaging, right? So you can use these because you can control the light that they absorb and emit. You can use them as tags, right? In a biomedical context, so that you can see certain parts of a molecule that you might be trying to tag or certain parts of a cell. And then it turns out they're also useful in other contexts entirely. So the light part of it can be useful in like an LED or something like that. So changing the color of your television. But then just nanoparticles in general might be useful for doing chemistry, right? So in all sorts of energy conversion technologies, nanoparticles are becoming very useful. So the field of nanoscience that was sort of started by those three people I showed before, has found a lot of use and is a really cool field. I think so. So the key takeaways from this presentation were that electrons are waves. That's what quantum mechanics says, and the frequency depends on the size of the material that they're in. Usually, materials are so big that there's no size-dependent effects, because you're not small enough, you're not close enough to the scale of the electron or the scale of the atoms for changing the size to do anything. But when you get really small, you do see those quantum effects. And one cool property, one cool quantum mechanical consequence is that you can actually change the light that's absorbed and emitted from a material by changing its size. And that gives rise to a whole bunch of technological application. And yeah, so that's the end of my talk here. That's the research group I'm in is on the left. My PI is David Limmer. It's a great group of people working in actually a whole wide range of areas in theoretical chemistry or physical chemistry. I work on nanoscience. I work on modeling how to build those nanoparticles that I showed. So sort of synthetic methods to get different shapes, different sizes. And the work that I do, specifically the grant that I'm on is funded by the US Department of Energy. And it's the Department of Energy funds a lot of our work. It's really a crucial funding source for us. One of the crucial national funding sources that we rely on to do this kind of work that has a lot of real world implications, a lot of technological implications. And so sort of the technological prowess of the United States is in many ways thanks to the research that's done on these types of grants in these types of fields at universities like UC Berkeley and at nationally funded labs like Berkeley Labs. I also write a lot for the Berkeley Science Review. So if you're interested in a more popular science topic, that's a popular science grad student run magazine that you could check out. And I'm happy to take any questions. Yeah.
So you were saying that the orbit of the electron is being limited by the size of that nanoparticle.
Yeah.
But I guess, like, first of all, like, I mean, if you do the exact calculation, and strictly speaking, the orbit is infinite, but it decays and it decays to the point that if you are too far from the nucleus, it's like negligible. Now I was assuming that the rate at which it decays is so that it's actually negligible a lot sooner than you reach the end of the nanoparticle. And secondly, like, if it does not decay that fast and somehow it is larger than the scale of a nanoparticle, which would be a big surprise, I don't see how the scale of a nanoparticle is going to terminate it, because I was assuming the opposite. It's all those wave functions that determine the scale of the nanoparticle, not the other way around.
Yeah, that's a great question. I glossed over a lot of the details. So I compared atomic wave functions to the wave function of an electron in a nanoparticle, but that's not exactly true. So let me see if I can try to explain this part. Okay, so you take all of the atomic wave functions that we had in the last slide, and you actually combine them all together when you bond these atoms together. And so you're not left with an atomic wave function, but actually, or an atomic orbital, but a molecular orbital. The molecular orbital extends across the whole molecule. So the molecule in this case is your nanoparticle. And just like you were saying, the wave function itself decays exponentially away from the molecule. So to put it more precisely, it's not that we're cutting off the wave function of an atom, but we're creating a new orbital with a different characteristic size, and therefore really a different energy gap between the ground state and the first excited state of that of those orbitals. It's
Okay, I guess I'm still confused because you said that somehow the size of a nanoparticle is limiting this wave function. That's the confusing part, because I thought that wave function, that you clarified that, okay, nanoparticle is the whole molecule, like molecule is the nanoparticle, a huge molecule. Okay, that's clear. But how are you saying that its size somehow is cutting off the wave function? I mean, I thought it's the other way around, like a wave function is going to determine the size of a nanoparticle.
So we are thinking of the nuclei of all the atoms as classical, and only the electrons as having a wave function. And so, as you were saying before, the wave function of the electrons, because they're bound to the nuclei of the atoms, decays exponentially away from the atoms. So therefore, where the atoms are determines how much spread is in that wave function.
Oh, so you're saying that nuclei basically limit affect how much electron spread. That's what you're saying.
Yeah.
Okay, that makes more sense. Okay.
Chemistry perspective. Yeah.
I would also love to hear, so you mentioned that you're also working on like altering the shapes of these nanoparticles.
Yeah.
And so does that mean, so like effectively the size of these nanoparticles is different from different viewing angles. So does that also then allow you to change kind of the different light that it'll interact with if you aim at different directions, or kind of what is the purpose of changing the shape?
Oh, that's an interesting thought. So when I was talking about this shape, I was thinking less about sort of the specific directions of the crystal, but about its like sort of general shape. So like having, instead of something that's approximately spherical here, having something that's like elongated like a rod, or like tipped in some way. And so as we were sort of discussing in the last question, what that would do is it would change the shape of the wave functions. And it would also change their energies. It would also give rise to other sort of other interesting optical phenomena. So there's something that's actually very useful for the biomedical imaging application that I talked about at the end, called a plasmon resonance. And so that's similar to what I was talking about with the electron wave functions, but it's where the electrons sort of oscillate on the surface of the nanoparticle. And so that would be, you can sort of give rise to that as you elongate the nanoparticles. That's just one example of how you would tune the properties with the shape rather than necessarily with the size. But it's just another tool to use in your toolbox. Yeah.
So to make nanoparticles, do you always need to use a conductor, or like do you need the electrons to be free?
No, not necessarily. So this, like I was talking a lot about metals like gold, but you can make like semiconductor nanocrystals that are actually super useful in a lot of technological applications.
I'm guessing they behave fundamentally a little different, right?
Yeah, they do. Yeah, so like you can have the general difference between like a semiconductor and a metal, but then you can tune the band gap of that semiconductor based on the size of the nanoparticle too.
So physically, what's the range of emission wavelengths that you can achieve? And like can we get these nanoparticles to say fluoresce at like UV wavelengths or lower than that?
I don't think you can change it by that much. I think you're yeah, I think you're generally near the visible spectrum.
Okay. Is that just like just how things, like, is that just a coincidence that like it's?
Yeah, I mean, I guess I'm not thinking about every possible material. So I mean, it's obviously going to be material dependent.
Right.
But yeah.
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 Can you go back to the very first slide where you show the cup, and on the right hand side, well, yeah, on the left, everything is kind of greenish, but on the right, you said that the middle is kind of more purple than the rest. Is it because the size of the particles in the middle is also different from the rest that this happens, or?
Yeah, I think in this case, there's a bunch of competing things. So there's both different sizes of particles, but also different types. So there's like gold and silver and aluminum, I think, in the cup. And so those would have different colors, but then they also have different sizes. So I think the purple was actually a different type of material. Yeah.
Other questions? Then let's give both speakers another round of applause. Alrighty, so thank you so much for coming out with this Popping the Science bubble. I'm gonna put up our QR code that I was talking about that you can use to join our listserv right here. Our next seminar is going to be again third Tuesday of the month next month, which is going to happen, which happens to be the 20th. So make sure you're right back here in just about a month's time. Anything else? All right, then. Thank you so much for coming, and I hope you have a wonderful month.
Thank you.